Hi and welcome to this next video from the Numerical Methods section, and in the previous video we looked at something called change of sign method, which allows us to find or to demonstrate there's a root in a particular interval. What we're going to do now is actually look at techniques to find the root, and the first of those techniques is iteration. So what I'm going to do is start off using a technique called trial and improvement. Now this was a staple on the GCSE spec. It got removed when we went to the new spec, so it might be you've not seen it. But this was a standard technique that used to be on there. And so we've got an equation, x cubed minus 3x minus 5 equals 0, and we've got to solve it. And solving with cubic is well beyond the remit of the GCSE spec, so we'll use the trial and improvement method. And we're given that x is in between 2 and 3. And it says here, give your answer correct to one decimal place. It was always one decimal place, so you still have to draw a table. Now, what I'm going to do quickly is say, well, let's just extend that. We'll do it to one decimal place to begin with, but then we'll have a think about what we need to do to find a root to a much higher degree of accuracy if we had to find it to 5 decimal places. But for now, we'll go for one decimal place. So let's go back, and you still have to start off with x equals 2, plug it in, end up with the minus, and say, well, okay, that's less than 0. So then if we did that with x equals 3, that's 13. That's greater than 0, so there's our change of sign that we talked about previously. So we knew there was a root in between 2 and 3. And then you'd go on and say, okay, well, let's pick another value. And you'd have a bit of a look and say, well, it looks to me, looking at these two numbers, it looks to me like we're closer to 2 than we are to 3. So let's just pick a value. So I'm going to pick 2.1 and have a look what happens to 2.1. Okay, that turns out to be negative. So we've got a little bit closer. So let's now go for 2.2. Chuck the value in. So x cubed minus 3x minus 5 when x is 2.2 is that value. That's still negative. What happens if x is 2.3? Well, it turns out to be positive. So now what we've done is managed to trap our value. We find our change of sign. We've trapped our value in between 2.2 and 2.3. So we know that we've now got a change of sign in that interval there. Now the final step you'd have to do in GCSE is then prove was it 2.2 or 2.3, and you'd be able to look at it and say, okay, well, we seem to be close there, but you'd actually have to try 2.25. I'm not going to do that for now. The point I want to illustrate is that this is not a particularly efficient way of doing things. It's taken us 1, 2, 3, 4, 5 calculations to get to this point, and we've now got accuracy to one decimal place. If we can imagine doing it to 5 decimal places, well, you can imagine the size of table that we'd need to be able to do that and the amount of calculation we'd have to do. So is trial and improvement a particularly efficient mathematical technique? Clearly the answer to that is absolutely no, it's not. We need something that's much better than just plugging in some numbers and seeing what happens. Unfortunately, that's what we're going to get to. We're going to get something that's much more efficient, and that's what iteration is. So there's exactly the same question again, and we're just now going to do the extension part of that previous task, which was find it correct to 5 decimal places. So here we go. We're going to use our repeated trials again, but what we're going to do is come up with a better way for deciding what our next or subsequent trial is going to be. So rather than just randomly having a look and going, okay, let's pick a number, we're going to use the outcome of one trial to become the value we're going to use in our next trial. In order to do that, we're going to need two things. We've got to have a starting value, which we've already been given. The starting value is x equals 2. And the other thing we need is a rearranged version of the equation. So let's do a bit of rearranging now. Let's make that say x is the subject to that equation. So what I'm going to do is do a bit of rearranging, and so we've got x is the cube root of 3x plus 5. Now normally we'd be going, well, that's not a solution to anything, because in order to find out x we need to know what x is, so we've kind of created a circular argument, but that's exactly what we need for iteration to occur. What I've done is change the notation ever so slightly. You see I've now got those subscripts in there, so we've got that one there, xn, that's our current trial, and that xn plus 1 is the next trial we're going to do after it. So we're going to use our value here to come up with a value, and then that value is going to be the next one we're going to plug in. So that's what that notation says. So here we go. We've got our initial value, x1, so x2 is therefore going to be this thing here with our value for 2 substituted in there. So let's do that. So it's the cube root of 3 times x1 plus 5. We know x1 is 2. Sub it in. Whack it into our cube root. There's our answer. And so now what we're going to do is say, well, x3 is going to be the cube root of 3 lots of x2 plus 5. So now what we're going to do is take our value from x2, this thing here, and we're going to plug it in. And when we plug that in, after a bit of kind of typing digits into a calculator, we end up with that. And already you can see we end up with 2.22, now we're on 2.26. So after only 2 calculations, it seems like we're doing better than we did previously with our trial and improvement. However, it's still a real ball ache having to kind of type these great long numbers into our calculator, so we can do a whole lot better using the calculator much more efficiently. So let's look at how we're going to use the calculator to speed this up. So there's my calculator. So what I'm going to do to start off with is I'm going to type in the starting value. In this case, the starting value is 2. Press the equals button, and we end up with that appearing on the screen. Now, what's happened now is that value for 2 is stored under ANS in the calculator's short-term memory. So now when I type it in, what I'm going to do, I'm not going to use that 2 anymore. What I'm going to do is I'm going to type in the formula, but instead of using the XN, I'm going to use the ANS key. So I'm going to type in something that looks like this. So we've got 3 times ANS plus 5 all within that cube root. And that ANS is 2, so press equals, and there's the 2.23. Now, on the calculator screen, we've already got 3 times ANS plus 5, but ANS is now this value, which is what we need. So when we just press equals again, the next one pops up. And so just repeated pressing of equals is going to give us repeated trials. So press equals, there's the next one. So if you try that in your calculators, hopefully you can see that working. So what we'll do is now go back to our previous screen and have a look at what we get. So there's our next value, and just pressing ANS each time just keeps chucking out these values, and you can see very quickly it's starting to settle down. We've now got 2.2790, 2.27901, and if we're looking at this, we want this to 5 decimal place. If we have a look at those two, x8 and x9, both have the same value to 5 decimal places, but more importantly than that, if you have a look at the digit after them, they will both round to the same thing as well. So what we're saying is the last 2 iterations gives us the same value, 2.27902 to 5 decimal places. So that means our answer to 5 decimal places is that value there. Cool. So we've managed that just by essentially typing in a starting value, typing the correct form into our value, and then just whacking the equal sign as many times as needed to spit out subsequent values, and away you go, and there you go. In an exam, it might be you just get to write down the first 3 or 4 values just to demonstrate that you know what you're doing. You don't have to demonstrate the technique in full, and you certainly won't have to write down kind of great big long lists of decimals up to like 8 or 9 decimal places. And so there you go. That's our first numerical technique iteration. It's a nice and simple one. There are a few other bits and pieces that you need to know about, but we'll have a look at those in the next video.